So now let's look at what happens to second excited state. So let's calculate for second excited state. Psi I2. Now we have 4q square minus 2. This is coming from Hermite polynomial, and the initial component is minus alpha q square by 2, right? Now this means that now this is symmetry of q square. Now symmetry of q square is totally symmetric representation, right? So that means this becomes, so for second excited state, it becomes, symmetry becomes totally symmetric representation, right? So that means A1, right? Or totally symmetric representation. Similarly, if you go to third excited state, you will again see that it will be forming symmetry of Q alone, right? So symmetry of Q will be again equal to symmetry of the normal coordinate or normal mode, right? So I can say and so on. So every alternate excited state will have symmetry of totally symmetric representation, and every other alternate will have symmetry of Q. Okay, that we can say. So because it is following symmetry of Hermite polynomials, which are even odd, and so on, right? So now we know the symmetry of ground state, we know the symmetry of excited state. Okay, now let us go back and look at the integral. So our integral is of the form psi 0 mu psi 1 star d tau. Now mu has symmetry of x, y, z, right? Psi 0 A1 or totally symmetric representation, and psi 1, if it is first excited state, let's say if it is first excited, symmetry of normal mode, or if it is second excited state, so this is for first. Let us only talk about first excited state. So now what will be the direct product of these three? So direct product of these three will not depend on this one because this is A1. So we have to consider the direct product of mu or the symmetry of xyz and psi 1. Now these will contain totally symmetric representation. The direct product, or I will write it down. So direct product of IR representations that has basis mu, which is x, y, and z, and tau 1, which is normal mode, will contain totally symmetric representation. Now this is again coming from direct product application. If and only if, let us call this as tau mu, and let us call this as tau psi 1. Tau mu is equal to tau psi 1, right? Then only it will contain totally symmetric representation. The direct product will contain totally symmetric representation, and the integral will survive, right? Integral will not go to 0. Only if tau mu is equal to tau psi 1. Now symmetry of mu is fixed. Symmetry of psi 1, we know what is the symmetry of psi 1. So that means the integral will survive. So this implies that integral will survive if and only if tau psi has x, y, z as the basis. either of the three, x, y, or z, right? X or y or z as the basis, because then their irreducible representations will be same as tau mu, and then the integral will survive. Okay, so now let us see what happens in case of water. So let us consider the case of water. So we have seen that the normal modes in water are 2a1 and b1. So two a1 modes are there and one b1 is there. Now let us try to find out the symmetry of a1, the basis of a1. So a1 has z as the basis and b1 has x as the basis. So that means if I'm now calculating the direct product of psi 0 mu psi 1, so I can say that psi 0 mu psi 1 integral d tau. So psi 0 has a1 symmetry. This will have b1 or a1 whether you're taking x or z component, and psi 1 has again b1 and a1, right? Whether you're taking which mode depends on which mode you're taking. Now in this case both the integrals will survive. That means this will also IR active, this is also IR active, right? So both the modes IR active. So again, I want to emphasize that although we have determined the vibrational modes, the normal modes of vibration using symmetry and group theory, not all modes will be active under IR or Raman spectroscopy, and we will have to set up this integral and find out using direct product whether the integration will survive or not, and that will define whether IR will be active or not. So basically here you will see all three modes in IR spectrum. Okay, now let us take another example quickly. So let us take an example of CH4 in this. So the normal modes, we have not done this case, we have not calculated in this class, but I would suggest you do it as a home assignment. So normal modes are A1, E, and 2T2. Okay, so these are the normal modes which we got. Now out of this, T2 is triply degenerate and has X, Y, and Z jointly as the basis, right? So that means the only T2 mode will survive here, other modes will not survive. So that means only T2 modes. So how many total modes are there then? 2T2. That means 6 modes are IR active, and A1 and E are not visible in IR spectrum, right? So this should be very clear now. So this is for IR spectroscopy. So now we have learned how to identify which modes which are observed, which normal modes of vibration will be actually observed in IR spectroscopy based on symmetry rules, right? Now let us, in the same lines, let us also continue this discussion for Raman spectroscopy. So In Raman spectroscopy, the only difference is that the integral, instead of now dipole moment, now you have polarizability, right? In Raman spectroscopy, the transition moment integral, that is m, changes to psi 0 alpha psi 1 d tau, right? So you can still write it as mu, and then mu can be written as alpha e, so you have e outside. So basically you are interested in the symmetry of psi 0, alpha and psi 1, right? So alpha, you can say alpha ij here. Alpha ij has 6 components. Remember the tensor, which is alpha xx, alpha yy, alpha yz. Sorry, we'll write zz first. Alpha zz, alpha xy, alpha yz, alpha zx, right? So alpha ij has 6 components, and if any of this component survives in this integral, the whole m will be non-zero and the mode will be Raman active. Okay. Now, what is the symmetry of alpha? Symmetry of alpha is basically the direct product of x and y and z, right? So, I mean x, y, y, z, any of these direct products, right? So alpha takes the form of quadratic function of the Cartesian coordinates, unit vectors, right? Which is in the form of x square, y square. We can write down x square, y square, z square, xy, yz, zx. Now here also psi 0 is a totally symmetric representation, right? So the IR for psi 0 is totally symmetric representation. IR is irreducible representation here, okay? Do not get confused with infrared spectroscopy, okay? So IR for psi 0 is totally symmetric representation, and psi 1 has the symmetry of the normal mode that we have already seen, and we are talking about only first excited state. You can, of course, you can talk about the second or third excited state if you want to, but let us keep our discussion to first excited state. So now we know the symmetry of all three. So now we have to see whether the integration will survive or not in a particular case. So now let's see the normal modes of vibration in H2O are, let's write it systematically. So you have A1, nu2 will be A1, and nu3 will be B1, right? Now for this one, the transition, so for nu1 and nu2, the integration or m will be equal to psi 0 alpha psi 1 d tau, star is assumed. Now psi 0 is A1, direct product. Alpha will have direct product as, so you have to find which of the alpha will form direct product as psi 1, okay? So now if I take alpha xx here, that is basically A1, okay? So you can have different alpha components from character table, but you have to choose which alpha which has symmetry as psi 1 star. So psi 1 star has the symmetry as, we know that it is symmetry of the normal mode. Symmetry of the normal mode is A1, right? So that means this integration will not go to 0. because it contains totally symmetric representation. Now for nu3, m is equal to psi 0 alpha psi 1 star d tau. Psi 0 is always a1 alpha. Now you have to find if there is any binary product of Cartesian coordinate unit vectors which has symmetry of b1. Okay, so now direct product with, I think this has alpha xz has the symmetry of b1. Psi 1 star has the symmetry of normal mode, which is b1. So again, this will not go to 0. That means all the three modes will be Raman active. So all three modes will be active in Raman as well as in higher spectrum, right? So now there is one very important rule. Okay, let's take one more example if we have time. Let's say, let us consider trans N2 F2. Okay, example. In this case, I'll tell you why we are discussing this example. So let's draw the structure. Now the point group here is C2H. You should be able to calculate that by now. So, and the number of vibrational modes, if you calculate, this will be, this is a non-linear molecule, so 3n minus 6. So this will be 3n minus 6. This will be 6, right? N is 4. So 4, 3 is a 12, and then out of 12 you have 3 translational, 3 rotational. So you are left with 6 vibrational modes, right? So okay, let's try to find out what are those 6 vibrational modes. C2H. So you have E, C2I, sigma H. Tau reducible, I'm directly writing tau reducible, so that will give you 12, 0, 0, 4, and this will be equal to 4Ag plus 2Bg. I'm skipping all the maths and I expect you to solve it by yourself. 4B4, right? So this is using reduction formula. So we have now obtained what are the symmetries of different vibrational modes, right? Now, which of these vibrational modes will be IR active and which of these will be Raman active? How would we tell that? So we know that tau vibrational is equal to 3Ag plus Au plus 2Pu. So this is the total vibrational modes, and then we have to actually find out the symmetry of vibrational modes from here by subtracting the translational and rotational components, right? So out of Ag, Bg, Au, Bu, so you can remove the symmetry of translational modes and rotational modes. So let's not do that. And I'm directly writing tau vibrational as this. Okay. Now Ag, what is the symmetry of Ag? So let us quickly look at the character table of C2G. So we are not even setting up the integration. I'm just opening a book and looking at the character table of C2H. So now C2H, if I see, this has the basis as Ag has the basis as x square, y square, z square, xy. Au has the basis as z, and Bu has the basis as x and y, right? So now you can see that this implies that Au and Bu modes are IR active and Ag modes are Raman active. So now there is a mutual exclusion between IR and Raman. So whatever modes are IR active, those are not Raman active, and whatever modes are Raman active are not IR active. So this is very important in spectroscopy, in IR Raman spectroscopy. So what is this mutual exclusion rule? This is the last principle, and then we'll wind up this course. So I'll say consider a molecule that has a center of symmetry. So if you notice, the molecule which we discussed, N2F2, has center of symmetry I, right? Or we can say inversion center. Center of symmetry or inversion. Now in this molecule, the unit vectors or x, y, z coordinates will be inverted through the center and will transform as Angirad representation, right? So their IR representation would always have U as the subscript, right? Because I, under symmetry operation I, X, Y, and Z will always have minus sign, right? So for minus sign under I, that means Angirad representation. Whereas we can say, on the other hand, binary products of X, Y, Z will not change sign under I operation, and thus would belong to Girard representation. So the IR representation corresponding to binary products of XYZ, any binary product, will always have +1 sign, because this will be essentially the direct product of the two component IR representation, which will have -1, right? So this will always form a Girard representation. XYZ will always form a basis to un-Girard representation, and thus whenever there is a center of symmetry in the molecule, the IR and Raman spectrum will be mutually exclusive to each other. So thus IR and Raman active modes will be mutually exclusive. So basically so whatever lines we observed in IR spectrum will not be observable in Raman spectrum, and vice versa. So that means, let's say if you are doing some synthesis and you want to know whether your synthesized molecule has center of symmetry or not. Let's say if you want to synthesize a trans compound and you ended up in cis compound or a mixture. So it is not a pure trans compound. Let's say the pure trans compound only had the center of symmetry. So now that can be easily tested by recording a simple IR and Raman spectrum of the same compound. Let's say if you find some lines which are common to both the spectrum, that means the molecule does not have I, or it has a contamination from a non-I compound, right? So that explains the mutual exclusion rule. And with this, we've come to the end of symmetry and group theory course. And I really enjoyed teaching you all. And I hope you have learned to the extent I wanted, and you have enjoyed the course as well. And I think that is all. And see you guys in the interaction sessions or in exams. If you have any difficulties during interaction sessions, please do ask, and see you guys in exams and otherwise. All right. Thank you. That is all for today.